In part 1 we built Newton's law of viscosity. Shear stress equals viscosity times shear rate. It works beautifully for water, air and light oils, but squeeze a tube of toothpaste or stir a bucket of cornstarch and it falls apart completely. These are non-Newtonian fluids, and most of what a real process plant handles belongs to this group. Here is what made a fluid Newtonian. Plot shear stress against shear rate, and you get a straight line through the origin. The slope is the viscosity, and it is the same everywhere along that line. Double the shear rate, and you exactly double the stress. For a non-Newtonian fluid, that line bends. The slope is no longer a single number. So we measure the slope at one specific point, shear stress, divided by shear rate, right there. That is the apparent viscosity, and it is only valid at the shear rate where it was measured. Quote an apparent viscosity without its shear rate, and the number means nothing. The most common behavior by far is shear thinning, also called pseudoplastic. At rest, long molecular chains sit tangled and randomly coiled. They resist flow strongly. Shear them, and they stretch out and line up with the flow. Now they slide past each other far more easily. So the harder you push, the thinner it gets. Look at what that covers. Paint, ketchup, blood, shampoo, and drilling mud. Every one of them thins as you shear it. It is exactly what you want from paint. Thin under the brush, then thick on the wall so it does not run. The opposite also exists. Shear thickening, or dilatant behavior. Cornstarch stirred into water is the classic example. Stir it slowly, and it pours like a liquid. Hit it hard, and the particles are forced together faster than the liquid can flow between them. They jam, and it behaves like a solid. Dense mineral slurries do the same thing. In a plant this is a hazard. A dense slurry that thickens under shear can stall an agitator or block a pump. Then there are fluids that will not move at all, until you push hard enough. Toothpaste sits in the tube against gravity. Squeeze it, and it flows. Below a critical shear stress, called the yield stress, it behaves as a solid. Above it, it flows. On the graph, the straight line no longer starts at the origin. It starts at the yield point. That is the Bingham Plastic model. The intercept is the yield stress, and the slope is the plastic viscosity. Toothpaste, mayonnaise, and drilling mud all live here. Two equations cover most of this. The power law, tau equals K, times shear rate to the power n. N below 1 is shear thinning, n equal to 1 gives Newton back exactly, and above 1 is shear thickening. Add a yield stress to the power law, and you get Herschel-Bulkley, the model most drilling and cement fluids are fitted to. One more twist. Some fluids change with time, not just with shear rate. Hold the shear rate constant. If the viscosity keeps falling, the fluid is thixotropic. Drilling muds and many paints do this. Leave them at rest, and the structure rebuilds. That is what lets some muds suspend drill cuttings when circulation stops. The rare opposite, viscosity rising with time under constant shear, is called Rheopectic. So for a non-Newtonian fluid, there is no single viscosity to look up. A useful number always carries three things with it: the temperature, the shear rate, and the model it was fitted to. Get those right, and you size the pump, the mixer and the pipework correctly. Get them wrong, and the plant will tell you soon enough.